Alright, so what I like to do in solving questions like these is just to first convert to SI units. This will help prevent us from making mistakes later on. So first step is 80 grams. That is the mass of the rod, and that is equal to 0.08 kilograms. Alright, what about 36 centimeters? We want that in meters. That's the length of the rod, and that'll be 0.36 meters. 12 grams. This time it's the mass of the clay ball, and it is 0.012 kilograms. And then 2.2 meters per second. That's our velocity. It is already in SI units. So now we can move on to solving the actual question, which is to what angle, measured from the vertical, does the rod with the attached ball of clay rotate? Now, when we have collisions of two objects, generally we want to consider momentum. So what is the momentum of the rod initially? Well, the rod is stationary, it's not moving. So we can deal with that later. What we have to consider right now is the momentum of the ball of clay. So what is that going to be? Well, momentum is mass times velocity. So in our case, it's the mass of the clay times the velocity of the clay. And this is linear momentum right now. But since it's going to hit that rod at the bottom, it is going to cause that rod to rotate, and we're going to start to deal with angular momentum. So let's look at initial angular momentum. We don't have to consider it for the rod right now. We're only looking at the clay. And that is the momentum, the linear momentum, times the radius. So we already have the linear momentum equation, right? That's just the mass of the clay times the velocity of the clay. And then we have this r here. So what is this r? Well, we are given that the length of the rod is 0.36 meters. And if that rod, right, this is the rod right here, if that rod is rotating about a point passing through its center, then what does that make the radius? It just makes it half of 0.36 meters. So the radius is 0.18 meters. So we can make our substitutions now. We have the mass of the clay, 0.012, times the velocity, which is 2.2, and then times that 0.18 meters for the radius. So what does this end up being? Well, this is 0.004752. So that is our initial angular momentum. And momentum in a closed system is conserved, right, without any external forces. So what this means is that our initial momentum is equal to the final momentum. So how do we find final momentum? Because now the rod is rotating. So it's making it a whole lot more complicated. So in order to find the final momentum, the final angular momentum that is, right, because it's rotating, we have to consider the moment of inertia. We have to consider the moment of inertia for the rod and the moment of inertia for the clay. And then if we add those two together, we're going to get the total moment of inertia. So what is the moment of inertia for the rod? Well, usually you're given these equations. It is 1/12 the mass of the rod times L squared. L is the length. So we can make some substitutions here. In our case, the mass is 0.08 and the length is 0.36. So the moment of inertia is 0.000864 for the rod. Then now the clay. Well, this time, we're going to consider the clay as a point mass. So it's just the mass of the clay times the radius squared. Right, why is that? Well, consider a point at the end, at the very bottom tip. Well, that is going to rotate around the radius r. So it's going to be mcr squared. And if we make substitutions, and then put that into our calculator, what we get is 0.0003888. And then, as I was saying earlier, we want the total moment of inertia. So we just add these two together. If we add them two together, we get 0.0012528. Right. But we haven't quite found the final angular momentum. The final angular momentum is equal to the moment of inertia, the total moment of inertia, that is, times the angular velocity. Now, what is the angular velocity? Well, we don't really know. We want to find that because we know this is equal to the initial angular momentum. So that means that the angular velocity is equal to the angular momentum divided by the moment of inertia. And we have these values. That leads us to the angular velocity being a value of 3.7931 radians per second, of course. So there we go. After all this work, we found that. But we're still not done, because we're looking for theta. So let's consider the scenario again. This clay is going to hit the rod, and at the moment just after the collision, the system has rotational kinetic energy and no potential energy, right? Considering the equilibrium to be 0. And then at the max angle, all of that rotational kinetic energy is going to have become potential energy. So what we should do here is find the initial energy and then set that equal to the final energy and see if we can somehow solve for theta. All right, so initially, our initial energy is the rotational kinetic energy, 100%. So that is 1/2 times the moment of inertia times omega squared. And we know these values. So if we solve for this, we have 0.0090124 joules. So that's our initial energy. And that is all going to be transferred into potential energy. So that is delta U, the change in potential energy. And what's the equation for potential energy? Well, that is mg delta H. And here we have the mass of the rod and the mass of the clay. But here's the thing. What is delta H for the rod? It's 0, right? Because the center of mass is not going to change. Delta H is the change in height, but it's commonly confused because it's the change in height of the center of mass, not the top of the object or the bottom of the object, right? Because maybe the size is changing. It's the change in height in the center of mass. So for the rod, it's delta 0. So we're only dealing with the clay here. So our equation is just going to be the mass of the clay times gravity, or G, right? And then times delta H. But what is delta H? Well, this is where our theta finally comes in, because we can use trigonometry and solve for theta, right? Because H is going to be equal to R cosine theta, right? Cosine theta is equal to H over R, so H is equal to R cosine theta. And what does that mean? Well, delta H is going to be therefore equal to R cosine of theta. Well, sorry. It's going to be equal to R minus R cosine of theta. So therefore, delta H is R times 1 minus cosine of theta. So we can make that substitution. We have MC times G times R 1 minus cosine theta. Make some substitutions. And we're going to get 0.0211896 times 1 minus cosine theta. And what is this equal to? Well, since kinetic energy, the rotational kinetic energy is equal to the change in gravitational potential energy, right? At the maximum theta, which is what we're trying to find. Then all the energy is going to be gravitational potential. So if we set this equal to the value that we found here, then what do we have? Well, just divide each side by this number here. So that will give us 1 minus cosine of theta equal, I'm going to go ahead and skip that math there, 0.42575586. So add 1 to each side. Sorry, subtract 1 and then times -1. So cosine theta is equal to 0.57424414. Take the inverse cosine. And that is 54.95328.397. So our answer is 55 degrees, right? Two significant figures.